The foundation of science, at its core, rests on the humility to continuously learn and revise our understanding of the universe, rather than on the arrogance that often accompanies accumulated expertise. This idea became especially relevant during my interview with Peter Doocy on the Sunday Briefing on Fox News yesterday, where I emphasized the simple but frequently overlooked principle that knowledge must remain flexible in the face of new evidence. When Comet experts reacted to the discovery of 3I/Atlas on July 1, 2025, many of them instantly categorized it as a conventional water-rich comet, simply because such objects had dominated their academic training and shaped their expectations over decades. Their reflexive response reminded me of the limitations of artificial intelligence systems. A machine learning model can only interpret new data based on the patterns found in its training set. If the model has never been exposed to a certain kind of input, it will naturally try to force that input into familiar categories. In much the same way, professional comet researchers, having spent their careers studying icy solar system bodies, instinctively tried to fit 3I/Atlas into the mold of the comets they already understood, instead of considering that it might be something fundamentally different. This problem is not a flaw in intelligence, but a flaw in the framework that intelligence relies on. Humanity has launched numerous technological objects into space over the past several decades, from spacecraft to scientific probes to satellites, and even experimental payloads like Elon Musk's Tesla Roadster. These objects now inhabit the same cosmic environment as natural celestial bodies. If we acknowledge this fact honestly, then scientists must expand their training data set when analyzing unfamiliar interstellar objects. The moment we treat our technological space debris and spacecraft as potential contributors to the catalog of objects moving through space, we make it possible to distinguish natural bodies from artificial ones. Without this adjustment, we risk misinterpreting potentially revolutionary discoveries simply because they do not resemble the familiar ice rock mixtures that dominated the traditional picture of comets. A powerful example of this occurred earlier this year. On January 2, 2025, the Minor Planet Center, which operates under the authority of the International Astronomical Union and is responsible for cataloging objects such as asteroids and comets, detected what was initially classified as a near-Earth asteroid. The object's motion looked consistent with a small rocky body orbiting the Sun, and so it was added to their database. Yet within just one day, officials examining its orbit noticed something astonishing. The trajectory of this so-called asteroid was an almost perfect match to that of the Tesla Roadster launched into space by SpaceX in 2018 as a dummy payload on the Falcon Heavy rocket. Once this connection was made, the designation of the object changed instantly. The Minor Planet Center removed it from the asteroid catalog and reclassified it correctly as a human-made object drifting through space. The ease with which a car wandering around the solar system was temporarily mistaken for a natural asteroid demonstrates how easily technological artifacts can masquerade as natural celestial bodies when scientists rely on outdated assumptions. This example highlights a broader point about the cosmos and humanity's very limited role within it. Elon Musk, inventive and influential as he undoubtedly is almost certainly not the most accomplished spacefaring innovator that the Milky Way has ever seen. Our galaxy contains roughly 100 billion stars similar to the Sun, and research suggests that approximately 10% of these stars host Earth-sized planets in the habitable zone where temperatures allow liquid water to exist. If we imagine rolling the cosmic dice billions of times across this enormous collection of Earth-Sun analogs, it would be statistically absurd to assume that our small civilization, barely a century into electrification and only decades into space exploration, somehow represents the pinnacle of technological achievement. Many of these other star systems formed billions of years before our own, providing an immense span of time for biological evolution, technological development, and interstellar ventures far surpassing what humans have yet achieved. To appreciate just how much time has been available to potential extraterrestrial civilizations, consider the slow but persistent journey of the Voyager spacecraft. Launched in the 1970s, Voyager carries the technological signature of humanity's early space age era. Even though its speed is modest compared to the theoretical possibilities imagined by advanced civilizations, it will, over the course of 1 billion years, traverse the entire galactic disk from one side to the other. 1 billion years may seem unimaginably long to us, but it is only a fraction of the age of the Milky Way, and many stars are significantly older than the Sun. This means that any civilization that arose millions or billions of years before humanity would have had more than enough time to send probes, artifacts, spacecraft, or other technological debris into interstellar space. Over such immense timescales, these interstellar artifacts would have had ample opportunity to drift into the solar system, passing near Earth just as our own spacecraft might one day drift near a distant star. The question is not whether interstellar artifacts could reach us, the laws of physics allow it, and the timescales permit it, but whether we are capable of recognizing them when they do. If our scientific community clings too tightly to old assumptions, relying solely on the patterns found in the study of local icy comets and asteroids, we risk misclassifying objects that may be indicators of advanced extraterrestrial engineering. A technological spacecraft or a piece of alien debris might not look like any comet ever observed before. It might move differently, respond differently to sunlight, reflect light differently, or exhibit unusual chemical compositions. Yet if experts insist on interpreting everything through the lens of frozen, volatile-rich comets, they may simply overlook the clues that point to artificial origin. This is why humility is essential, not in a philosophical or moral sense, but as a practical requirement for scientific progress. Humility keeps the mind open to possibilities that lie outside the familiar patterns. Humility encourages scientists to question long-held assumptions and to treat anomalies not as errors to be dismissed, but as opportunities to expand human understanding. Modern science has advanced primarily because great thinkers dared to challenge the prevailing models when observations no longer fit comfortably within them. The discovery that Earth revolves around the Sun, the recognition that continents drift, and the realization that quantum mechanics governs subatomic particles all emerged when scientists were willing to reconsider what they thought they knew. The arrival of interstellar objects, especially those that behave differently from standard comets and asteroids, represents another such opportunity. If we approach these anomalies with open minds, supported by rigorous observation and a willingness to incorporate new forms of evidence, we may uncover aspects of the universe that previous generations could not even imagine. But if we remain bound by outdated training data, our interpretations will be limited and our discoveries muted. In the same way that artificial intelligence systems cannot recognize something that lies outside their training set, scientists who refuse to broaden their intellectual framework cannot identify phenomena that fall beyond the boundaries of past experience. The universe is too vast and too varied for us to assume that we have already sampled every category of object it contains. Interstellar visitors may come in many forms: rocky, icy, metallic, artificial, or something entirely unknown. Our responsibility as a scientific species is to recognize when we are facing something new and to investigate it with curiosity rather than prematurely categorizing it based on habit. For this reason, the arrival of 3I/Atlas should not be treated merely as another comet to be cataloged and forgotten. Instead, it should be seen as a reminder that our cosmic environment is not limited to natural debris. Just as the Tesla Roadster drifting through space confused experts when they first identified it, so too might unknown interstellar artifacts confuse future astronomers unless they are prepared to consider a broader range of possibilities. The universe does not care about our prior assumptions. It simply presents reality as it is. Our role is to observe it honestly, question it boldly, and interpret it wisely.